Welcome to the Journey Shake Cam. I am so excited today. We get to do lab. But before we can do lab, we have to do the warm-up. And today's warm-up will help you in doing the calculations in your lab. You're given a data table and you need to come up with the Hydrate formula. So give it your best shot and we'll talk about it in a moment. In order to determine the formula for the hydrate, I must first figure out how much of the anhydrous compound that I had. Now I'm given in this data table the mass of the hydrate, the mass of the evaporating dish, and the mass of the anhydrous compound with the evaporating dish. Well, I know if I subtract out the evaporating dish from the anhydrous compound, that will give me the mass of the anhydrous compound. And when I do that subtraction, I get 1.21 is what I started with. And I get 0.61 grams of the anhydrous compound. Now we know from the description that you were given in the warm-up that the compound is nickel 2 sulfate. And I must change my grams to moles. And 1 mole of nickel 2 sulfate has a mass of 154.8 grams of nickel 2 sulfate. And I could do that here. Nickel has a mass of 58.7. Sulfur is 32.1, and I have 4 oxygens, which is 4 times 16.0. I'm going to write them again, 58.7, 32.1, and 64.0, and when I add them up, I get my 154.8 grams per 1 mole. And that's how I change my grams to moles. And when I do this math, I find out that I have 0.003940 moles of the nickel 2 sulfate. Now, in order to know how to get the formula for the hydrate, I must determine how much water was in the hydrate. Well, I know that if I had the hydrate that was 1.04, and the mass of the hydrate anhydrous compound is 0.61. That is the anhydrous compound. The difference is my mass of my water. And therefore, I take my mass of my water and change it to moles. And 1 mole of water has a mass of 18.0 grams of water. Oxygen is 16 and each hydrogen is 1. The total is 18.0. And this gives me 0.02388 moles of water. Now, the next thing I must do is divide by the smallest. Well, this number is much smaller than this number. Therefore, I divide it into both numbers. And I get 1 nickel 2 sulfate and 6 waters. The ratio of the anhydrous compound to the water is 1 to 6. That is the ratio. The empirical formula for the hydrate would be nickel sulfate with a dot and 6 waters. That is how we write the hydrate formula. We do not put the water inside here. If we did that, it would look like this. Whoops. You'd have 12 hydrogens and 10 oxygens, and you would not recognize that compound and that it has the water inside that crystal. So we do not do this. we have to separate it out by multiplying the number of water molecules inside of that crystal. And this is what we'll be doing today in the lab. You were asked to determine the moles of each and then the formula for the hydrate. Now, I hope that that helps you when you're working up the numbers in the lab, and I will see you in a moment. Now, I am so excited to be back in the lab. I could almost do a dance, but I have to control myself because we've got to get down to business. So here I have my balance, and it's set to 0. I'm going to weigh out an evaporating dish and find the mass of the empty evaporating dish. And it is 41.91 grams. 41.91 grams is the mass of my empty evaporating dish. Now I'm going to set this to 0 because I'm going to weigh out exactly 2.00 grams of my hydrated crystal. Isn't that beautiful? That just reminds me of the ocean, the Bahamas. Oh, I gotta get back. Okay, so here we go. We're going to measure out 2.00 grams, and I can put this here a little bit. I could also use my spoon when I want to become more exact. Oh, we're over a gram. Getting close. Very, very close. We never pour materials back into the original container. I have to have my excess container. Now, this is just a tiny little bit. 2 point, oh. I want it to stay at 2.00. 2.00 grams of my hydrated crystal. Now you need to look in the objectives to find out exactly what this crystal is. I have 2.00 grams of my hydrated crystal. Now I get to see at the Bunsen burner. Here we go. Oh, here we are at the Bunsen burner. I love the Bunsen burner. Now, I've got my goggles on, as I always should in the lab, but today I don't have to tie my hair back. It's mighty short. Now, I'm going to light the Bunsen burner. I take my striker, I turn on the gas, and get some spark going, and there she goes. Now, I think I want a little bit higher flame, because I'm always impatient. So we'll just, now, did you see that beautiful color of that crystal? Well, we're gonna drive off all that water from that hydrated crystal. And as always, just like when you're cooking, you must be patient. Sometimes when we make fudge, we have to stir and be very, very patient. And as you watch, you will see this blue color will begin to disappear. And that will show the water, because the water is reflecting the light, making this crystal blue. And it will get lighter and lighter. Now, just as though I was cooking, I have to have patience. If I want a thick gravy, I've got to stir and stir and stir. It doesn't just happen overnight. I just can't put the flour in the pot and expect it to happen. You have to be patient. Now, what I'm looking for here is I must get the mass of the anhydrous crystal. That's the crystal without the water. And we know that the hydrated crystal had a mass of 2.00. We want to know what the mass of this crystal is without the water. So that just like in the warm-up, I can get the moles of the anhydrous compound and the moles of the water, and I can get my empirical formula. Now we know that the ratios must be around 0.1, give or take 0.1, and therefore if it's not close to 0.1, I will have to multiply. And I can see how that crystal, the water is going away. It almost looks like an island in the middle of the ocean. It's very, very interesting. And it's almost like there's a little puddle of water. That's amazing. And I'm timing it, and we're supposed to allow for approximately 10 minutes for this crystal. However, the time just gives us an idea of approximately what we can expect. And in actuality, I can observe when it seems that the water is gone. However, sometimes there could be water there and I can't see it because they're molecular. They're very, very tiny and not available to the eye. I have to have something to go by. Although I can see that the edges are becoming more brown and the middle is getting lighter and lighter, almost like a green. In chemistry labs, we have to be patient. We're always trying our patience. So we grow our personality, we grow to get more and more patience. You know, doctors like patience too, but they like a different kind of patient. But anyway, that's kind of funny. Maybe not so funny. But I like to watch this crystal. And when you're writing up the lab, remember that you have to have the title, the objectives, the procedure, the data table. Any conclusions or further investigations must also be answered. And you're going to need to get the theoretical formula for the hydrate. And actually, it's not theoretical, it's the experimental that we're determining today. And the theoretical would be what we had on the very first worksheet when we did the example problem, because this hydrated compound is copper 2 sulfate. And it actually has a 1:5 ratio. But we'll have to use our masses to determine what our experimental hydrated formula will be. And we just have to be patient and wait for all that blue to go away. Go away, blue. Now, you know, in the movies, we could always fast forward it, but then you wouldn't get the joy of sitting and watching the experiment. And that's a very important part, because we have to learn on these things what it actually entails to be watching this lab. And this is the very first of 3 labs in our lab marathon. Today we're doing the hydrates. Tomorrow we'll do the empirical formula for magnesium chloride. And the last day we'll do potassium chlorate, one of my all-time most favorite compounds. And I can see that this is getting lighter and lighter, and the blue is getting further and further away as all the water is coming out of those crystals. The Bunsen burner is pretty hot, and therefore it goes pretty quickly. But you have to have a special setup to be able to have a chemistry lab. This would be very difficult for you to do at home. But what we're doing is standard procedure. And when you go to college, you'll know exactly what the equipment is, what the process is, and some of the tips of how to do these things. And we just have to be patient. But today's warm-up, I cannot emphasize enough how important it is for you to use today's warm-up to be able to write up your lab and determine your experimental formula for this hydrate. This lab is very, very basic, and it's very important for us to start with a very basic one. And tomorrow's empirical formula is a pretty well-known one as well. And then potassium chlorate will be graded on accuracy. So we'll hope that your professor, that would be me, the Shea Chem, is going to do it very accurately. But you can't always count on that. That's why they're experiments. And sometimes we can have very, very good lab technique, but still the results aren't that good. So we just have to go with what we got in the lab. That's the way that goes. Now, remember, we never use calculations as a source of error in our lab. We have to use things like what could have gone wrong in the lab. Well, in this lab in particular, maybe I don't heat it long enough. Maybe I'm not drying out all the water, driving off all the water out of that compound. Or maybe I'm going to dry it too much. That's also a possibility, and it might then be a difficult problem. Now, what are some other sources of error that we could have? Well, if we were measuring on the scale and we took it off when it was 1.99 and we expected that it was 2.00 and we recorded the 1.99 in the data table versus the 2.00, that would also create some errors in our results. The biggest errors, however, for this is not heating it long enough to drive off all of that water. That's primarily the big one that happens here. And remember, even though it seems like most of the water is gone, that doesn't mean it's all gone, because sometimes I just can't see those water molecules. They don't just pop up and say, hey, I'm still here. That would be nice if they did, wouldn't it? But they don't do that. No siree, they don't do that. But we're getting close to the time. I can see that that light green is showing me that a lot of that water has gone. Now, we never accept weighing something warm as one of our sources of error because that could damage the scale. We don't want to do that. And also, when you take the measurement of something that is warm, hot air rises, and that would cause the evaporating dish to be buoyant and our mass to be less than what we would expect. We never want to weigh things warm. We want to make sure that they are definitely room temperature. However, we do want to measure this immediately as soon as it's cooled because there might be moisture in the air. Some areas of the world are very, very humid, and it would be very possible for the water to get back in to the compound. It wouldn't take very much. And that would also cause an error in our results. I just have to be patient. Remind myself for that patience because I want our results to be as close as possible. We just have to wait and hope that all the water comes out. Crystals are all looking greenish green. How green is greenish green? Well, I don't know. There's a lot of different colors of green. Chartreuse, I always think chartreuse is red, but chartreuse is green. And this is definitely green. Sometimes, while we are always monitoring the Bunsen burner, we can never walk away from a Bunsen burner. And if we have a partner, they could monitor it while we walked away. But somebody needs to always be watching the Bunsen burner. However, we could be working on our further investigations or our conclusions while we were waiting for this to heat up, because I always like to make the best use of my time. I might as well work on some problems now instead of waiting till later and then I have all kinds of other stuff to do. Just wait. Can you hear that Bunsen burner? That flame's mighty hot in there. It's just going crazy. You just gotta love lab. That's, chemistry is a lab science, so that's why we must do labs. We have to find the experimental values and do our lab because it's a major part. 20% of our overall grade is labs, and we gather the data together and then you write up the lab report and give it to your facilitator, and they'll take it from there. Well, this calls for a decision. The person doing the lab has to decide, is it dry? Is it not dry? Has it burned long enough? Has it been heating long enough? Or should it heat longer? Well, whenever in doubt, heating longer is always a good idea. I don't want to use a stirring rod to stir this because then I get some of my anhydrous compound on the stirring rod, and that would really definitely create another error in my results. Well, all the blue is gone out, and I believe that it's been approximately 10 minutes. I just get so nervous. I'm like, I don't know, should I take it off? Should I not take it off? Well, I suppose we'll go ahead and take it off. So I'll turn off the gas, and I can use my fancy hot hands. They almost look like they're going to talk to you. And I take it off, and I can set it on the lab station. Oh my, I got that wire gauze as well. But that's okay because these lab stations are made to handle hot items. And I'll just let it sit, and we'll let that cool down, and I'll see you at the scales. Now we have let the evaporating dish cool completely. Remember, we cannot weigh anything that is at all warm. It must be completely cool. And then I'm going to put it on the balance in the middle of the pan. And it has a mass of 43.21 grams. 43.21 grams. Now, the reason it's fluctuating is because it's probably right in between the 1 and the 200th place. But it seems to be on the 1 more often. So we'll go with 43.21 grams of the anhydrous compound and the evaporating dish. And those are the numbers that you need in order to complete this lab. You use those numbers and make sure that you write up the lab with all of its parts: title, objective, procedure, data table, conclusions, and any further investigations for one formal lab report. Well, that was fun, and you know how much I love doing labs, and tomorrow we get to do another one. That is so exciting. So there you go. You need to make sure that you start working on those labs, and I can't wait to see you tomorrow. Bye.